Let's continue now with Chapter 12. We want to discuss the concept of foundation settlement. So what causes foundation settlement? It's going to occur when the soil compresses beneath whatever load is being applied. The greater the compressibility of the soil, the greater the settlement. For coarse-grained soils, that settlement will be immediate as soon as the load is applied, and it will usually occur during the construction of the building. But what happens or causes settlement in fine-grained soils? Normally, these are our clayey soils. In this case, part of the settlement will be immediate. The other part will occur over a period of time, possibly months or years, and we call this consolidation settlement. It will occur because the water that is within the clay particles is slowly squeezed out, and the soil will collapse on the space taken up by the water and will shift. One way to prevent that would be to replace the soil, put our foundation below this fine-grained clay unstable soil, or to put a surcharge on the soil. Basically, a load of soil that might remain for 1 or 2 years, and its weight will compress the soil and squeeze the water out, and in essence pre-settle the water. There is a study done by the Wisconsin DOT on settlement prediction that I have posted to Blackboard. It is 178 pages, and I will confess to have not read it all, but it is there for you if you are interested. And if you do read it, I suggest you do it digitally and not print out all 178 pages. Here's an example of what happens. There is no settlement. Here the settlement is uniform so that the building simply sinks into the ground. And here's differential settlement where we may get cracking in the building. Our text tells us of Mexico City Palace of Fine Arts that was built in 1934, and the city's increasing use of groundwater has caused the building to sink almost 14 feet. In their case, they were fortunate that it's been a uniform settlement. Now, mat or raft foundations will have negligible differential settlement of this nature because of their rigidity. Sometimes the dimensions of footers will be based on settlement and not bearing capacity. So let's talk about foundation drainage. Water is not our friend, not in this situation. It will accelerate wood decay. It will promote the growth of mold and fungi. If I get water in the soil and foundations, it will increase the lateral pressure on basement and crawl space walls. It will corrode reinforcement in concrete and masonry. Might cause the heaving of soil during freezing weather, and can cause the flooding of basements and crawl spaces and provide breeding grounds for mosquitoes. Clayey soils are very vulnerable to excess water because of their shrink and swell characteristics. Here in Northeast Ohio, we can speak to that, can't we? Now, 2 types of water will affect buildings. Surface water. Now, this is water that's coming from rain and snowmelt, or subsurface water. So I can control subsurface water by making sure my ground slopes away from the building. Usually 4% slope is adequate, but the farther you can take the water away from the building, the better off you will be. Subsurface water control is usually required only in buildings that have a basement or crawl space, and I want to reduce the water pressure on those walls. So I install drainage around the foundation with a perforated drain pipe, crushed stone or gravel, perhaps a filter fabric, and that captures the soil particles and keeps them from clogging up the pipes. Or I can use a number of terms. French drain, trench drain, footer drain are all used for this type of drainage system. And people learn as they go along. My house was built at a time when a perforated drain pipe was installed. Crushed stone or gravel was placed over the first 18 inches or so, and then the rest of the basement wall was backfilled with the native soil. The thinking today is that the crushed stone or gravel will cover the drain pipe up to 18 inches from the surface, and then native soil is backfilled. The reason is we want all this stone here to let that water drain, and this being a very clayey area, not have that water collecting in the clay soil, creating pressure on the basement wall. So what do we do when we have a stable soil? Okay, we can have a reinforced concrete slab on grade or slab on ground. Foundation walls with interior piers, elevated ground floor, and wall and column footings on the ground floor that create a reinforced concrete slab. In the reinforced concrete slab on grade, the trench is the formwork. It's cost effective. It will work only where the frost depth is not an issue. However thick it will be based on the soil capacity and the load. And if shrink swell properties of the soil require it, we may use a raft type foundation. And this is what it looks like. I think we saw a picture of this when we were talking about concrete. Basically, we're excavated to the base of the mat, and then these trenches will form a rib to strengthen the concrete slab. Again, another depiction of how the slab on grade is created. So where I'm using exterior foundation walls, now this is used where I have a deeper frost line. Colder climates, deeper frost line. Remember, the frost line is where the depth below the surface that the soil will not, the water in the soil will not freeze. This is our typical Northern Ohio basement. We have strip footings under a load-bearing wall. Interior columns support intermediate beams. And again, the crawl space or basement, footer, masonry wall. Here is the foundation system, an isometric of the exterior foundation wall system. Ground floor was going to be wood, might be a crawl space or a basement below. I love this. Cover it with a rat slab. That is so encouraging. Here's the sill plate. We'll talk about that when we talk about the wood light frame construction. The joist or floor joists, subfloor, and this would be either the basement or the crawl space. Again, a section through a exterior foundation wall system. Well, what if we have an expansive soil? These are normally used on low-rise buildings, sometimes used where the soil has a low bearing capacity. A post-tension concrete slab on grade foundation, grade beams with drilled piers, grade beams and drilled piers with a suspended concrete floor slab, or drilled piers with a suspended concrete floor slab. The post-tension foundation, similar to the ribbed reinforced slab on ground we just talked about, except instead of normal rebar we use high-strength steel. It will also consist of perimeter beams and intermediate beams in both directions. And except for the tensioning, it will look just like the reinforced concrete slab on grade. The post-tensioning is going to increase compression in the slab, so it stiffens the slab, will prevent the development of cracks, and it does not require control joints because the post-tensioning will cover that. So again, here are the components for a drilled pier support. And remember, this system is used for a building on expansive soil. In this case here, the reinforced concrete beam transmits the load from a bearing wall into the foundations that are spaced, such as a drilled pier or a caisson. And again, reinforced concrete grade beams. Frost-protected shallow foundations. Book used to talk about this. They don't now, but I wanted to go over it very quickly. Slab-on-grade foundations, deep frost line, incorporates insulation around the perimeter and uses the heat that escapes from the building to keep the temperature of the slab above the freezing temperature. And it will raise the depth of the frost line under a building's foundation. So you can see my heated exterior here. This would be where the frost line normally is, and what it does, it warms this soil and keeps it from freezing. And some ways to do it. And here's another section using a concrete masonry wall. So we define a basement as an enclosed space below the ground floor of a building. Residential basements are generally 1 floor deep, floor height of 8 to 10 feet. Now, keep in mind that some building codes state that living spaces must be 7 feet 6 inches or more of ceiling height. Hence, some basements are only 7 feet and therefore do not qualify as living spaces. We'll terminate the top of the basement wall 2 to 3 feet above the finished ground level. It will vary. If the site slopes, I may have the basement floor above the ground level on 1 or 2 sides, and we call that a walkout basement. You're going to find residential basements more common in colder regions, and that's because the frost line is deep enough that the basement becomes economical. Because since the frost line is deep enough, the excavation for the footings to go below the frost line is so close to a full basement that, well, you might as well do the extra excavation. Now, Commercial basements might be several floors deep. Think back to the story I told about Link Hall at Syracuse University. If I waterproof the side of the wall with direct exposure to the water, basically the outside of the basement wall, that is known as positive side waterproofing. Negative side, the waterproofing is on the opposite side, that is from the interior. And usually it's only going to be used in remedial applications. Blindside waterproofing is applied to the outside of the wall that will eventually become inaccessible after the wall's construction. Usually in this case the basement wall is supported by some sort of excavation support system that we talked about in Chapter 11, such as soldier piles and lagging, and are usually left in place. So here's positive side waterproofing. This has been excavated out. The waterproofing is applied to the outside of the wall, and then this is backfilled. Here's blind side, where the waterproofing is applied to the shotcrete, and then the basement wall is built right up against the mat. So in this case, the waterproofing is applied to the support system and not to the wall, and the wall is built right alongside of it. Again, here's waterproofing. Here's the shotcreted surface, and you can see it's in different stages of construction. Another view of it. Here's positive side waterproofing. This is at the Boston Center site. You can see there's a mastic, a tar applied to it, and then an insulation applied around the side of it. So just as diversion in terms of deep construction, I wanted to show this to you. It is from this was a commemorative book put out in 1904 by the Interborough Rapid Transit Company on the construction of New York City's very first subway. We have here the support of an elevated structure so that construction of the subway can take place below it, usually with something called cut and cover. The street was excavated and in some cases might have been decked over so traffic could continue above it while the base and the walls of the tunnel were built, and then the roof or cover of the tunnel was finished, and then as the decking was removed, the tunnel was backfilled and left in place. Here is a method of creating a diversion. This was a sewer system, a very large sewer system, and the subway would transverse it, and rather than change the level of the subway or the sewer, which of course is dependent upon gravity, 3 smaller pipes were installed to handle the flow while the train went across it. And this is the subway going through the Times building and the different supports that were needed in order to get the subway through and keep what was above it from collapsing. Now, the Times Tower was originally constructed on a location known as Longacre Square. Longacre Square is where 7th Avenue and Broadway cross, creating these little triangular squares at each end of it. By 1872, it had become the center of New York's horse carriage industry, but didn't have a name. So the city named it Longacre Square because there was a location in London, England, known as Longacre, where the horse and carriage trade was centered. Now, in 1903, the publisher of the newspaper, the New York Times, came along and used this section of Longacre Square to build the newspaper's new headquarters. The publisher was quite powerful, caught the ear of the city, and said, well, this new subway that you're building, why don't you have a stop right here by my building? And so, having done so, the square changed its name to recognize the newspaper and hence became Times Square. And here's another example of cut and cover. In this case, it's an arched concrete tunnel, and you can see the backfill starting over it. And this is an interesting concept. This was a tunnel section. It was a 2-track tunnel section, and before the subway was opened, it was determined to make it a 3-track tunnel section. So they tore down this wall and built a new wall out here and then extended the cover of the tunnel. But again, this is underground construction at its supreme here, and I thought I'd share that with you. And that ends chapter 12.